Hi, in this short video, I'm going to show you how to use Mathematica and Laplace transforms to solve ODEs. So we're going to start with the simple example. Okay, first we want to find the Laplace transform of this function, which is t squared times a unit step function. So how do we enter that in Mathematica? So you can go Laplace. The command for Laplace transform is Laplace transform square bracket. You can go t caret 2, and then you can type in unit step square bracket t minus 3, and then comma, it's a function of t, you want back a function of s. You shift enter, you'll get the Laplace transform of that. Now you can easily copy this. Okay, we can save this over here. I'll save it in a variable a, press shift enter, and then we can do inverse Laplace, and I'm doing this for a reason. A comma, it's a function of s, you want back a function of t. We should technically get this function back, but let's see what we get back. Shift enter, okay, and you get t squared times heaviside theta function. So let's see what this heaviside theta function is. So let me plot that. Plot, okay, heaviside theta square bracket t minus 3 comma curly brace t comma 0 comma 5. Oops, I forgot a square bracket. And you can see it's exactly the same as a step function. And remember, the step function was developed by Oliver Heaviside, so that this function is named for him. It is 0 up to 3, and then it comes on and becomes 1. So it's the exact same thing. So heaviside theta and unit step are one and the same. Okay, so that's how we take Laplace transforms of step functions. The next thing we want to do is graph piecewise functions. I want to graph this piecewise function, which I'm going to use later to solve the ODE that I did in class earlier today. Okay, so to do that, you create a function g square bracket t underscore square bracket g square bracket t underscore square bracket colon equal to, that's how we create functions. That's a format in Mathematica. Piecewise square bracket. Now, the way piecewise function is done is you have to supply a list and close the square bracket for the piecewise function. So within that list, you have to supply each piece in curly braces. So comma, curly brace, comma, curly brace, because I have 3 pieces here, 1, 2, and 3. So the first piece tells me the function is 1, comma, if 0 is less than or equal to t is less than 1. The second piece tells me the function is -1 if 1 is less than or equal to t is less than or equal to 2. And then the third piece tells me it is 0 if t is greater than 2. So that's how we create a piecewise function. You put in each piece in a curly brace, and then you write down the value of that function, comma, the domain of that function, and so on. So let's type in shift enter, and that creates that function for us. So let's plot it. Plot g of t, comma, curly brace t, comma, 0, comma, 5, and then close the parentheses, and that'll give us that function. So it's on, it's at 1, then it becomes -1, then it becomes 0 after 2. And you can see it's clearly a discontinuous function. Okay. If you want, we can find the Laplace transform of this directly. We can come out and we can go Laplace transform of g of t, comma, it's a function of t, I want back a function of s. Got a bracket here. There we go. And that gives us the Laplace transform of that function. Now it uses hyperbolic sines and cosines to do that because they're all exponentials in a way. But if you wanted to, we could write it using unit step function and then tell it to find the Laplace transform. So let me go ahead and do that. So if you recall, the way we do that is Laplace transform. So the way we do that is we type in 1, and then in curly brace you type in u of square bracket t minus 0, okay, because that's when it comes on, correct? And or you can just type in u of t because you have to put the 0 in. And then it goes off at u of 1, so you go at 1, sorry, square bracket t minus 1. And I'm doing u, but it should be what, unit step. And this should also be unit step. Okay, so that's what we have there, close parentheses, plus it's minus 1 now in the middle, so you go minus 1, open parentheses, unit step, t minus 1 minus unit step, t minus 2. So that's there, close parentheses, plus it's going to be 0 after that, so we don't really need to write that. And this is going to be a function of t. You want back your function of s. Okay. And that's what we get. So if you were to simplify this, I'm hoping we'll probably get the same thing. Let's try that, see if it'll keep using brackets. 2 / simplify. And we get that if you were to expand this now. So we do this, simplify and expand. Because of that square, and expand that. And we get exactly what we have at the bottom. So sometimes Mathematica might give you some goofy looking answers, but if you work with it enough, you can use other Mathematica commands to get it to the way you want. But anyway, so that's how we graph a piecewise function. That's how we take a Laplace transform of a unit step function that we showed you earlier. And we're going to use this g that we just did to solve this ODE using Laplace transform step by step, just like you would do by hand. So I'm going to do it. So the first thing we're going to do is define this ODE. So we're going to go ODE 1, 1. It's problem 1, step 1. That's how I'm naming it. Is equal to y double prime of t plus 4 times y of t. Okay. Equal to. Remember, we're defining this ODE just like we typed in Mathematica. When you say two things are equal, we put double equality, single equalities for assignment. G of t, which is this function, the step function that I have here. So I'm going to copy this. Control C, come out here and paste it. Okay. And that's going to be my ODE right there. The initial conditions I'll supply later in a second. So if I press Shift Enter, now ODE 1, 1 contains that ODE. So if I want to, the next thing, what would we do? We would take that ODE and take Laplace transforms on both sides. So let's do that. Laplace transform, actually. This is step 2. So I'll go ODE 1, 2. Problem 1, step 2 is equal to Laplace transform of ODE 1, 1, comma, it's a function of t, comma, s. I want the Laplace transform of that. And we get, did I not press Shift Enter here? Shift Enter, syntax error. Parentheses, oops, I forgot a parentheses. Oh, there we go. Okay, that's better. And it spit out the ODE. So this ODE 1, 1 contains this. If you put a semicolon, excuse me, it'll suppress the output. So you won't see that. Now we can run this and you get the Laplace transform. Now in class, if you notice, it's calling this Laplace transform y of t, comma, s. We call it big Y. Mathematica doesn't know that, so let's give Mathematica some help in figuring that out. So I'm going to call it ODE 1.3, step 1.3 is equal to, I'm going to take ODE 1.2, and then I'm going to put a / dot. What that does is, that basically, actually let's do this all together instead of creating a separate step. What that's going to do is, we're going to use this command here. Now that we know this, we're going to come out here at the end and type in / dash. In Mathematica, this is a command. It tells Mathematica to replace something in the expression before that, in this previous expression, with something you're going to tell. So I'm going to tell Mathematica to replace Laplace transform of y of t, comma, s with, use a dash and a greater than sign, big Y. So it's going to come in this grayed out answer and replace wherever it sees Laplace transform of y of t, ts, it's going to replace it with big Y. So this is called a replacement operation in Mathematica. So if you press that, we'll get that, which is exactly what we wanted. Now, if you wanted to replace these initial conditions, which is also what we want to do, I can come out here and put curly braces, because now I want to replace more than one thing. So I'll do that, put a comma here. I want to replace little y of 0 with 0. That's my initial condition, comma, y prime of 0 with 0, and close curly brace. Now, because we have more than one thing to replace, we're going to supply a list of things we want to replace. So we're going to replace this y of 0 with 0 and y prime of 0 with 0. So let's press Shift Enter. And is neither a list nor a, okay, what is this having? Oh, I put an equality here, greater than, remember, we got to put an arrow here. There we go. Now it should do it. Perfect. So we got y's, we got rid of all the other stuff. So the next thing we do by hand is we solve for big Y. So let's do that. I'll call this ODE 1.3 equal to, we use the solve command in Mathematica. In ODE 1.2, we want to solve for big Y. So that's what we're going to supply. So it's going to do that for us. Perfect. Now, we want to take the inverse Laplace of this, but we don't want to take the inverse Laplace of these parentheses, curly braces, and this y and the arrow. So we want to extrapolate just this piece here. If you recall, anytime you want to get something from a list, this is called a list. You type in 2 square brackets open and 2 close square brackets, and within that you supply some values. If I supply 1, it'll give me the inner list. So you notice it got rid of the outer parentheses, curly braces. If I come and put a comma 1, it'll get rid of the other 2 curly braces. And then if I come and put a comma 2, it's going to give me just that function on the right of the arrow. And there we go. So that's good. Now 1.3 contains that. So we want to solve that now. I'm sorry, we want to take the inverse Laplace of that. So I can do inverse Laplace. We don't have to do partial fraction decomposition. Mathematica will do that all for us. We do 1.3 comma t comma s, but that's not right. We want to go from s to t, and then we want to save it into something. So I'll call this ODE 1.4. Okay. So it'll save it in there. So press Shift Enter. And once again, you notice Mathematica gave us these Heaviside functions, but that's okay. We can work with that. We can come out here and just do what we did out here with replacing here. Okay, so we'll do the same thing. We'll come out here, put a / dot. This time we'll replace the Heaviside function, Heaviside theta, with dash and greater than with unit step. So we're going to tell Mathematica to replace all the Heaviside theta in the answer it gave us with unit step that we are used to. There we go. And there's your answer to that ODE, to that differential equation that we started with the initial value problem. Now, it would be really nice if we can get this looking like a piecewise function again, but there's a nice command in Mathematica to do that. It's called piecewise expand. We want to expand this last one, ODE 1, 4, close square bracket, and I'll expand and give that to us. There we go. If t is less than 1, it's this. If t is between 1 and 2, it's that, and so on. Now, if you were to try to graph this piecewise expand, you'll notice the graph does not look as nice as we want. Okay, if I were to do that, like, I'm sorry, not piecewise expand, ODE 1, 4. So let's graph that and see what we get. Plot ODE 1, 4, comma, curly brace, t goes from 0 to 10. Okay, so let's see what we get. Oh, actually, did a good job. The old version of Mathematica always left a gap. The reason for that is because Mathematica concluded that 1 is included and 2 is not, and out here it's assuming that t is greater than or equal to 2, so I guess it did graph this. In my old version of Mathematica that I have, it doesn't graph these things correctly. Okay, maybe if I shrink it, you might see the gap. Oops, comma. Nope. Usually I get a gap at 2, so this is perfect. We can graph that function. You can see the piecewise expand everything. You can see our solutions are continuous, and that's how you solve the differential equations using Laplace transform in Mathematica. You can do it step by step so that way you can check your work as you're doing it by hand. If you have any questions regarding this, please come see me and I'll be happy to help you.